available to you if you didn't bring the PowerPoint today. Now the PowerPoint is helpful, but I will deviate from the PowerPoint a little bit. So we'll just keep that in mind too as we're going through. All right, solutions. At this point, solutions, we've already talked about solubility. Now this next unit with solutions in acids and bases considers things that are soluble. Certainly the idea of precipitate forming comes into play, especially when we get into calculations that involve how much of a precipitate that you can make. But you already have the idea that solutions are made from something that you're taking, and usually an ionic salt, and you put it into water and it dissolves, right? So that's the big picture of what solutions are all about. And now we're going to take that one step further and go into calculations with solutions. So solutions is something that's homogeneous. It's a single phase. There's not two phases like oil and water. And you have a solute and a solvent. The solute is usually the thing that's in the smaller proportion, the minority concentration substance. The solvent is the thing that is in the majority of concentration, the thing that you have more of. They call water the universal solvent. Remember, solute over solvent. Water is the universal solvent because it dissolves most ionic substances. And in the lab, probably 70 to 80% of what you're going to come into contact with in the lab are ionic substances, salts that are metal-non-metal combinations. So water will dissolve most of these things. So examples of solutions could be gas and liquid solutions. If you have a soda pop, that used to be my favorite morning drink when I was in college. I like coffee now, but I used to like Coca-Cola. I still like that taste of that aluminum-y-ish Coca-Cola in the morning when it's nice and cool. But gas in a liquid is a solution. There's liquid-liquid solutions. You could take, say, for example, vinegar and water. Those mix homogeneously in infinite proportions either way. You can make a liquid-liquid solution. You can even have a solid that is considered a solution. If you have jewelry that's like 14 karat, 12 karat, 24 karat, that carat measurement is the proportion of gold over the proportion of other lesser metals. They put lesser metals in gold jewelry so that it's not as malleable. If you had pure gold in your gold jewelry and you knocked it on something, it would bend and it would misform very easily. Gases in solution affect just like solids in solution, except in opposite ways. When you want to dissolve more of a solid in solution, say for example you have iced tea, right? And you want to dissolve more sugar in it. If the iced tea is warmer, you can dissolve more sugar into it, right? Gases are just the opposite. The solubility of a gas decreases as the temperature increases. And I'm sure you've seen that. If you leave a soda pop out and it goes from cold to warm, it gets what we call flat, right? And when it's flat, all the bubbles have come out of it, and that's because the bubbles decrease. The amount of gas that is soluble in a soda decreases as the temperature increases. So solid liquid solutions, you can increase the amount of solvent, the stuff you put in when you increase the temperature. Gas liquid solutions, you decrease the amount of gas you can dissolve in a solution. The idea of pressure influences gas solubility. Now, we haven't really talked a whole lot about gases yet. That's the last chapter we're going to talk about. But in gases, everybody has a little bit of an intuitive feel because we all have gas in our tires. We all exist in a sea of gases, and we've all had soda pop of some kind. And so this idea of vapor pressure or pressure of the gas is expressed by Henry's law. Now, we're not actually going to do calculations with Henry's law in this class, but we do when we get to 151. What dissolves depends on what you put into it. This idea of chemists call it like dissolves like. Now, in the molecular geometry unit, we talked about two kinds of molecules. We talked about polar molecules and nonpolar molecules. Now, in this example, when we say molecules, we're talking about covalently bonded substances, non-metal combinations, which is really the minority of stuff that you're going to come into contact in the lab, but the majority of stuff that you come into contact with in your everyday life, right? We breathe air, which is covalent or covalently bound substances. We have water. Those are molecules that can exist on their own. So there's polar molecules and non-polar molecules. Water is really polar, and that's why it dissolves most ionic substances, which are also polar. So things that are polar will dissolve in water. Things that are non-polar will dissolve in non-polar substances, like benzene is a very good non-polar substances. Any of these things are things that you would look at in organic chemistry, and in things in the right-hand column, non-polar things. Polar substances are things like water. If we take oil, if we take something from the second category, from the nonpolar substance, and we try and put it into the first category, they're not going to dissolve. It's like oil and water. People think that oil and water don't dissolve in one another because of the density differences. No, the density differences cause the oil to be on top and the water to be on the bottom because oil is less dense than water. But why they don't mix is because oil is very nonpolar and water is very polar, and the nature of the substances won't allow them to mix because of the fact that one is polar and one is nonpolar. So that's what gives us this idea of like dissolves like. Methanol, or anything with an OL, alcohol. In organic chemistry, you'll learn a lot about the different long-chain hydrocarbons. And methanol will dissolve in water, but it won't dissolve in oil or in hexane. Hexane and toluene will dissolve in each other, but hexane and water won't dissolve in each other. So like dissolves like. Ionic compounds, something like a salt, that's a metal-non-metal combination. You put it into water, which is a polar solvent, and it will dissolve. If we put something like sugar in water, it appears to make a homogeneous solution, and to the untrained eye, Joe average on the street, you might say that that has dissolved. But as a chemist, we say sugar is not soluble. It will dissolve, but it's not soluble, meaning the molecule doesn't break up. You can see sugar is generally made of carbon, hydrogen, and oxygen in lots of different proportions. That's table sugar, but there's fructose, maltose, lactose, anything with OSE on the end of it is considered a sugar. And they're all different combinations of carbon, hydrogen, and oxygen. You can put them in water, and they will appear to make a homogeneous solution, but they don't actually dissolve. However, you can take sugar and put it in a nonpolar solvent like gasoline. That used to be something that people would do before locking gas caps were invented to ruin somebody's car. They would put sugar into your gasoline, which was soluble in the gasoline. It would mix with the gasoline, go into your engine, and cause all kinds of problems with your engine. Well, locking gas caps has solved that complete problem, but it wouldn't work the same. Like if you put salt in gasoline, it would not dissolve because salt is an ionic compound, has a metal-non-metal combination. A good example of this is you can take salt, put it in water, and you put a conductivity apparatus in it, and the light bulb will light. A conductivity apparatus has two electrodes, a positive and negative, and is attached to a light bulb. And when you put it in something that conducts electricity, the light bulb will light. If you take salt, regular table salt, and put it in water, and the conductivity apparatus will light, but if you put sugar in, it won't light because there's no ions in solution, and you have to have ions in solution in order to conduct electricity. So this idea of the dissolving process happens when water molecules jump onto the surface of, let's see, did I put I have a link in here. I think I still have, there it is. Okay, this is a good link to show the process. And I know we've talked about it before, and I probably had a similar slide or similar link in another slideshow. Let's see what this one has. I found this one. That was really good. Molecular geometry. There it is. There's the water molecule looking like Mickey Mouse. Has a bent molecular geometry because it has those non-bonded pairs of electrons on the other side. So there's a salt crystal, sodium and chlorine, and it's in a cubic structure that ionic compounds are. And there's the water molecule with the red parts being hydrogen, the blue parts being oxygen, and the positive side of the water molecule. Yep. Oh, you can't see it, can you? All right. Well, here I can see it really good on mine. Let me shut this off. Let me shut the animation off here. Oh. Thank you for telling me. Here I was looking at my screen. There it is. Let's see if I can minimize this.
And no Larry.
No, we weren't.
It's not liking that. All right. Well, we might. I'll leave the link in there, and you guys can go back in and look at it. But what it does is basically of course, Larry's not here.